got a little intro that I've put in for the entropy unit. The thermodynamics and entropy preview, which you've got here, has an associated PDF. The outline, the videos, and the web assigns and the readings will cover this unit completely. This intro is just to get you a little bit comfortable so you can see where we're going with this. Look it over and I'll give you a better feeling. It's certainly not a complete description of entropy. That's what the outline is for in the other videos. But this is worth a few minutes. So let's go to the introduction. Chemistry, we've always said, is a study of change, where we start with some stuff and we get some new stuff. We've always looked at the initial, how things change, and finally what we end up with, usually an equilibrium. We've looked at rate, where we've got this lowercase italicized k that will tell us how fast it's going to happen. And we've also looked at concentrations and amounts using the capital K italicized, which was the equilibrium expression, where if we had a reaction that had some sort of equilibrium, in this case I chose A reacting with B to make AB, we start off with something, we change it, and we reach an equilibrium. And at that equilibrium, if we look at the concentrations of the products over the reactants, we end up getting a constant for a specific temperature. This is a pretty powerful thing that we've gotten. We've spent a few weeks on it. We've even applied it to acids and bases. Got our KEQ, and also this Q, which is going to show up again. It's our reaction quotient, where we put in the numbers that we have, and to see what the answer is, Q, and we compare that to the equilibrium constant to see, hey, is it at equilibrium or not quite there or over the case? Well, we're going to come up with something new. It's delta G. It's referred to as the thermodynamic favorability of a reaction. Chang ends up calling it in most textbooks, and most people refer to it as the spontaneity, how spontaneous a reaction is. AP likes to use the difficult to pronounce thermodynamic favorability and a lot more to type. Change in G, because this is typically used as a change, just like enthalpy, where we look at the reaction at the beginning and then at the end, and we look at the reactants. We say, okay, this is where they're at, and then we get to our products and say, okay, how is this going to end up changing? We compare the two. Now, the delta G ends up having this little superscript on it when they talk about standard state. And this is important to remember. The sign of delta G will end up giving you the direction a reaction goes. You'll notice I put question marks here because, hey, is this reaction going to go forward or is it going to go backwards? But we have to establish where we're starting at. This is our reaction. How is it going to go? Well, the reaction has to indicate what we're starting with. This 0 indicates that the quotient is 1. That what we're starting off, if we're going to start this race, this tug of war between reactants and products, and that's what it is. Everybody starts off at 1. 1 atmosphere or 1 molar. In other words, this is something you got to remember. The initial setup in this chapter and the next chapter is that we start with everything off at 1, where Q is 1 over 1 over 1, and I don't care if you square it, your reaction quotient is going to be 1. So this is where everybody starts. If everybody is here at 1, we've got 1 molar products, and we have 1 molar reactants. What's going to happen? This G is very, very powerful for that. So the two things that we're going to deal with delta G is the very important sign. Ask the questions on this delta G. Is it a plus or is it a minus? The next thing, it's going to end up giving us an energy value. Kilojoules per mole of reaction. They refer to this as the free energy. In fact, this is called the Gibbs, named after Josiah Gibbs, one of the great American chemists, as free energy. And this is the Gibbs free energy is the name of it. I don't like the term free energy, even though it's used all the time, because no such thing as a free lunch. It would be better if they would have said the available energy to actually do work. In other words, we're going to have energy, kilojoules, for every mole that's listed in the balanced reaction. But these kilojoules are the kilojoules that will actually do something, that you can harness to do something with. We've heard kilojoules before. In fact, this kilojoule per mole of reaction showed up here in our change in enthalpy, changes in potential energy. and we would have drops of potential energy, and we'd get heat from that reaction. Here I've got two reactions that are both combustion reactions. We've got hydrogen and oxygen making steam, two gases exploding to make water vapor, and carbon, coal, and some oxygen making carbon monoxide, both gases. We've done problems with these before where we used enthalpies of formation and all sorts of other little tricks to find out, using calorimetry even, what's the heat in this reaction. For burning hydrogen and oxygen, there's 242 kilojoules for every mole of steam that's made. For burning carbon to make carbon monoxide, you get released as kinetic energy because we have a drop of 110. But when we try and get this energy from a reaction, we find that we can't get the 242 to do things. Now, this is where we end up dealing with work, and I'm going to explain that more carefully. If you really want to harness this to do something, if you want this to power a car, move it, if you want it to power your cell phone or run an engine, you're not going to get 242 kilojoules that are available out of this heat to actually do something. In the case of hydrogen and oxygen, we only get 228.6. Now, you might think that's a small difference, but no matter what you do, no matter how carefully you do this reaction, even though you get a drop in potential energy and an increase in kinetic energy of 242 kilojoules, you can only get 229 out of it to do something. In this case, the carbon monoxide, we get 111 kilojoules of heat, but you can harness this reaction to get 137 kilojoules of energy to do something. So delta G will be the actual work, the available work. And they say that's the free energy. It's free to do something, but I prefer the actual work. That gives free energy will be the actual work you can get from the reaction. Now, the example I have here is Mars lander, Perseverance on Mars. It was traveling at 300 kilometers per hour. Its parachute had slowed it down to about 200 miles an hour. They had to slow it down some more. They had to slow it down to a couple of miles an hour, otherwise it'd smash into the ground. And they used retro thrusters. They burned hydrazine. They had a catalyst. Hydrazine decomposes into nitrogen and hydrogen. You get a loss of potential energy of negative 50 kilojoules for a mole of hydrazine liquid hydrazine as it decomposes. That's the change in enthalpy. But these thrusters are effective enough and to get 131 kilojoules of work done. Joules are defined by applying a force over distance. So these thrusters are forcing and slowing down this thing, and you get this much energy out of it. Delta G is a very, very important thing because you want your cell phones to work. How much work can I get my cell phones to do from these batteries? You want rockets to work. You want a car engine to get work to move things. In fact, even your body, your ATP and ADP end up doing work so that you move around. That work is described with the Gibbs free energy. So this is a big deal. They saved it for the end of the year. On the thermo section of the AP equation sheet, there are three equations that deal with Gibbs free energy. One of them has enthalpy in it, and we'll get to this later. Another one has the equilibrium constant tossed in it, and the other one has voltage, E, batteries in it. And we'll cover this last equation in the next chapter. Let's deal with delta G. Gibbs available, Gibbs free energy. First of all, the sign is critical. Delta G negative, less than zero when it's negative. This means that the reaction is favored in forward direction. So here we've got the reaction I had before. A plus B becomes AB. Notice I said the arrow is now pointing to the right. It's not an equilibrium. If you calculate the delta G, and you'll learn about calculating it in the chapter, if you get a negative value, if everything starts off at 1, remember this is our tug of war, the reaction is going to happen. It's going to go forward, you're going to make AB. You're going to get a negative X, and a plus X to reach equilibrium. Now we talked about hydrogen and oxygen burning to make steam, and we get this negative 229 kilojoules for every mole of steam that's made. Ability to do work. This reaction goes forward so well, and here's one equation that you're going to see. If you take the delta G, the Gibbs free energy, negative 228, change its sign. This sign here is important. And divide by 2.5 kilojoules, you get E raised to that power. This is going to be like E raised to 100. And your K, your equilibrium constant, is 4 times 10 to the 39. I mean, if this reaction happens, it goes totally forward. You may even have an atom or two of these things left behind if you start off with stoichiometric amounts. That's how unequilibrium this is. This reaction goes forward. And in fact, if you get a Gibbs free energy of greater than 25, you can pretty much use, hey, it's happening, and it's going forward. We're not going to have much of our reactants left stoichiometrically. It'll be like all product city. The reverse. A positive delta G. If you've got a positive delta G, then the reverse reaction is thermodynamically favored. And again, remember, we're starting from 1. Don't forget that. Everybody's starting at 1. That's the fair way to do things. If you're going to predict, is this reaction to go forward or backwards, don't do it with just reactants. Have the reactants and products there ready for this tug of war. If your delta G that you calculate becomes positive, then the products, which were at 1, will go back into the original reactants. Now here I've got a reaction where hydrogen and iodine react. This is a reaction where the Gibbs free energy is 2.6. Now when you calculate the equilibrium constant for this, you end up getting, again, we take this 2.6, we put it in here, and change the sign to a negative. We're raising E to a negative value, which is going to mean it's going to be less than 1. Remember, E to the 0 is 1. E to a positive number is greater than 1. And E to the negative, just like our logs, is going to be less than 1. So our K is only less than 1. It's 0.355. And the K is the products over the reactants. So we're going to lose some of our products. They're going to no longer be 1. I did the calculation. It's one where I had to use solver. And you wouldn't be expected to figure out, but I wanted to show you what happens if you have a positive Gibbs free energy. Notice we started off at 1, and this wasn't a huge Gibbs free energy. And we lost some of our hydrogen iodide, and notice I did it stoichiometrically. Our change is always stoichiometric, 2 to 1 to 1. And when we're done, when we've reached equilibrium, we have no longer 1 for our hydrogen iodide concentration. We have 0.687. And we have now more hydrogen and iodine. So a positive delta G, and if it's a small value, it's not going to be much of a change, but it will have this reaction go backwards. Now, why? What makes delta G tick? Well, here it is. Here's the equation. This is one of the most important equations in terms of figuring out what's happening. Is this going to happen or not? I mean, that's a big deal in chemistry. Well, delta G involves just 3 things. If the delta H is negative, we've got an exothermic reaction. If this delta H is negative, that means we get a negative delta G. So a exothermic reaction where we take weak bonds and snap them together to make really, really strong bonds, where we have the rock roll downhill, that is thermodynamically favored. It's spontaneous. It's going to happen. A negative exothermic reaction is good news in terms of if you want to make products. There's our enthalpy, and that sort of makes sense. We've got delta G in kilojoules per mole. Delta H was kilojoules per mole, so everything is good. Now, I said 3 components. What's the other 2 components? Well, notice we got a negative sign here. So this negative sign is going to multiply these other 2 components. And again, negative means spontaneous, thermodynamically favored. Second factor, temperature. Now, temperature is in Kelvin. Don't use degrees Celsius for this. So it's always going to be positive because you can't have a negative temperature. It's a multiplier. And at room temperature, and that's what this 0 stands for, room temperature, 25 degrees Celsius, 298 Kelvin. Even though sometimes we will do a little bit of changing on that, and you'll see about that later on. We've got our change in enthalpy. We've got a temperature multiplier, and we've got a negative sign here. What's this last thing? Oh, we get another letter, S. And logically, S stands for entropy. Yeah, I know. They're not going to use E. This is what the chapter focuses on. The change in entropy, E-N-T-R-O-P-Y. They made this confusing. We've got enthalpy, which is H, and we've got entropy, which is S. Oh, wow. But hey, it's chemistry. It's supposed to be difficult. So now for the S. S's entropy is hard to describe. Even our textbook is sort of vague in what entropy is. In the AP curriculum, they use a specific description. It isn't exactly 100% bulletproof, but will follow, and it's good enough. Remember, this is our last factor in the Gibbs available energy. It is of a measure of how spread out or dispersed the energy and matter of a system is among different possible ways that the system can contain energy. It's our textbook, and a lot of textbooks, they talk about microstates and, believe it or not, shuffled cards. It's one of these things that's really difficult to explain, but once you see it, you can sort of understand it. It's almost as if we have a natural understanding of what entropy is. Some people refer to it as a measure of randomness. In fact, I do. That's the way I always think about it. So here we have got enthalpy. This is interesting. You can actually measure how random something is. We know that the randomness factor of a perfect crystal at 0 Kelvin will be 0. It's going to be perfectly unrandom. Now notice the unit here. It's joules per Kelvin. Immediately, flags should go up saying, wait a second, delta G was in kilojoules, and entropy is in joules, so you're going to have to change this entropy into kilojoules. Now, these problems can be a little bit involved. Don't mess up your units. Change the entropy into kilojoules. I wish they would measure entropy in kilojoules, but they don't. Now, back to how much randomness do things have. I put this table together so you can compare entropies. Remember, 0, perfectly ordered, 0 entropy. Here you've got a diamond, one of the densest molar substances there. A lot of carbon atoms packed together in a beautiful, beautiful tetrahedral arranged crystal. Its entropy, in terms of joules per Kelvin, of course mole, is only 2.4. That's getting close to 0. In fact, when I look up tables, diamond is almost always the lowest random substance around. It's got the lowest entropy. And the table that I was looking at in our textbook, the highest randomness of molecules was dinitrogen tetroxide, which is almost as difficult to say as thermodynamically favored, which it is, because it has a entropy of 304. And notice I said it is favored, even though energy is conserved. The law of thermodynamics is that the entropy of the universe is increasing. Now, the AP describes changes in entropy, and that's what they're really worried about, changes in entropy. Entropy increases when matter or energy becomes more dispersed. That's the AP definition. Not perfect, but that's the one that they use. If you answer an FRQ, that's what you got to say. If somebody says, why does this thing increase entropy? You would say, it is increased when matter becomes more dispersed. So solids going to liquids, that increases entropy. And wait a second, let's go back to our equation. If S gets larger, if the change is positive, following the rule of the universe that the entropy of the universe increases, this is a positive, times the negative, that makes this factor negative, which increases our Gibbs free energy. You want more Gibbs free energy? You want to be able to do more work? Make its entropy increase. So, you want a reaction to have a negative delta G? Go forward, change a solid into a liquid. Change a liquid into a gas. Dissolve something. Now, there are some exceptions here, and we'll run into those later. This one really needs a footnote, and read that footnote. Increase the temperature. Yeah. Getting more particles. If you break things apart, if you dissociate, if you decompose, your change in moles is positive, you're making things more random. Mixing of particles and forming molecules. If you mix stuff together, it's more random. We've got our equation, Gibbs free energy. You want more Gibbs free energy? Exothermic reaction. You want more Gibbs energy? You want a reaction to go forward? You increase the randomness. And they come together. They both are involved. We'll also use this to prove why a negative delta G gives us a large K. Now hit the chapter outline. I hope it makes sense for you. And we've got some great videos here for you and a web assign on that. Good luck!